All right, welcome back. Let's get started, shall we? In this video, we're going to finish up section 1.6 from our textbook with a discussion about reducible second-order equations. Now, a general second-order equation could be thought of as looking like f of x, y, y prime, and that's what makes it second order, and y double prime. And so we're saying that in some cases this can be reduced to a first order equation, and then we can use techniques we already know to solve that differential equation. So the first example we want to look at is with the dependent variable missing. Now, this is a function that I would think of as a function in the variables x and y, and I've sort of habituated myself to at least writing myself a note that looks like that to remind me that my variable list is x independent variable and y dependent variable. So if the dependent variable is missing, we would mean that y is missing. And if that's the case, then the equation that we're looking at looks like f of x, y is missing, y prime, y double prime. And our substitution is going to be to let p, arbitrarily chosen here, equal y prime. Now if we do that, then y double prime would be equal to p prime, and I see that my equation would look like f of x, p, and p prime, which is a first order differential equation, and the variables would be x and p. P would be the dependent variable, x the independent variable. So I don't know, that seems like maybe that's fairly straightforward, and I guess we'd ought to give it a try and see if it works out as straightforward as what it appears. And so let's look at problem number 43, and that's at least about on page 72 or 73, somewhere around in there. So the equation is x, y double prime equal y prime. And when I look at that, good inspection, look and note, it's a second order, and the dependent variable y is missing. So what I hinted at a bit earlier is that maybe we want to let p equal y prime, and then y double prime would be equal to p prime. And let's see, here's our differential equation. So now let's substitute. And when we substitute into our differential equation, we get x, y double prime would be p prime, equals y prime would be p. Well, this is a first order, and it's in fact a variables separable differential equation. So if I rewrite this just using algebra, I can rewrite this as 1 upon p dp is equal to 1 upon x dx. And this is why it's variable separable. It's variable separable because I can separate the variables, which I've done. So after we separate the variables, the next thing we would do would be to integrate the left-hand side and the right-hand side, and we would get a natural log of p is equal to a natural log of x plus a constant. I'm going to call that constant C1, but you could call it uppercase A, and you'll see that in the textbook they do use an uppercase A, but in either case it's an arbitrary constant. Now this we can exponentiate both sides, and if we do that we'll get a P is equal to CX. And you of course will want to satisfy yourself that that's correct. Now we're going to back substitute, and when I back substitute, P is what? Well, P is, where do we write it down at? We wrote it down right here. P is y prime, and so when I back substitute, I've got y prime is equal to CX. And this was, I put a 1 on it earlier, so let's keep the 1 on it, C1X. And this is a first order. And it's variable separable again, isn't it? First order variable separable. So I can separate those variables and write dy is equal to C1X dx, and then integrate both sides, and you get y is equal to C1 x squared over 2 plus C2. Now C1 over 2 is an arbitrary constant, so I could rewrite this as y is equal to C1 x squared plus the C2. And that's going to be the solution to the original differential equation. And as an exercise for you, you could show that this is a solution. One other thing to note here is that this solution has got two arbitrary constants, which is why I called one of them C1, because I knew I was going to have another one that would be a different arbitrary constant. So this is a general solution, and it's got two arbitrary constants, and that would be a characteristic of a general solution for a second order differential equation. Second order, two arbitrary constants, and we've got them both here. And if you would take the derivatives and find you've got y, find y prime and y double prime, and substitute in the original differential equation, you'll find that with arbitrary constants C1 and C2, this is a solution to the original differential equation. So that was, I guess, sort of as easy as advertised. Now there's another kind of second order reducible equation. So let's call this second order reducible equation, and the key here is going to be the independent variable, which is x, is missing. So the equation would look like f of x is missing, so this would be y y prime, y double prime equals 0, and the substitution is going to be, well, we're going to let p equal y prime again. Let's see, I'm going to write the p first. Oh, I'm so happy I've got an eraser. So this is going to be p equal y prime. Now, that much is quite familiar, but it gets a tiny bit different after that. So this would mean that y prime would be equal to p, and now we've got to be careful. Y double prime would be dp dx, which would be dp dy times dy dx. That would be using the chain rule. The chain rule is one of the most useful rules that we have. And here I've got a dy dx, and dy dx is y prime, which is p. So then I would just rewrite y prime is equal to dy dx is p, and dp dy, dp dy. So now I've got a differential equation that looks like it's written in y, and y prime is p, and y double prime is p dp dy. So this is a differential equation with independent variable y and dependent variable p, which kind of explains what we're differentiating with respect to. And if you look here, the derivative is dp dy. That's a first order differential equation. So we've taken what was a second order differential equation, and by substitution we've made it into a first order differential equation, which we hope we can solve with methods that we're already familiar with. And we're going to try one and just see how well this works out. So let's go to page 73 in problem number 51. And I'm going to get a sip of water before we start. So this equation is y double prime is equal to 2y y prime cubed. And this is a second order differential equation, and what's missing is the independent variable x. There's no independent variable x. So we know from this material at the top here of our screen that we would like to let p equal y prime, and then y double prime would be equal to, just like right here, y double prime would be equal to p dp dy. So I would have, now doing the substitution, in my original differential equation, and I guess I'll box that so we can find it easily. I would have y double prime, which would be y double prime is p dp dy, and that's all on the left hand side, is equal to 2y, and then y prime y prime would be p, and that would be cubed. So here is a differential equation. I recognize it as such because it's got a dp dy in it. That's a first order differential equation, and it's in the independent variable y and the dependent variable p. So maybe we can use the techniques we already know to solve this equation. Well, let's see. Looking at it, I notice that this thing is variable separable, and let me just rewrite it algebraically, and I'll put in steps that you would do in your head, I suppose, but it's okay to put in some extra steps here. Is equal to 2y dy. So you divide by p cubed, and then I've got all the p's over on this side. The dy goes with the 2y. So you know what that looks like. That's 1 upon p squared. So I've got the integral of p to the negative 2 dp is equal to 2y squared over 2 over 2, and then plus a constant. This time I'm just going to use a as the constant. Maybe that's easier than using C1 and C2, although of course it doesn't matter. So what's the integral of p to the negative 2? This would be p to the negative 1 divided by negative 1, so this would be negative 1 upon p is equal to, and the 2's cancel out, so this is y squared plus a. And now if I would back substitute, this is p. Let me make that tail a little longer. Negative 1 upon p, well, p is y prime, so this would be equal to, question is how many steps do I want to put in? Negative 1 upon y prime is equal to y squared plus a. Now I'm going to multiply through by negative 1, and as I do that I get 1 upon y. I know that many of you can do a whole lot of this in your head. This would be a y prime. But I want to emphasize that when I multiply through by negative 1, I get a negative y squared minus a. But a is an arbitrary constant, so negative a would be an arbitrary constant also. I might as well just call that a and absorb the negative 1 into the constant a. But that would not be true of the y squared. I can't be quick and loose with the negative on the variables, but I can with the constants. All right, so then what next? Well, next I would take the reciprocals, and so this is all of course. Even better, I like this as y prime equal negative 1 over y squared plus a. So that's the same thing. I just changed my mind about where to put that negative sign. And I think that makes the rest of this a little easier. So what do I get if I multiply both sides by this denominator? I get y squared plus a, like that, dy is equal to negative dx. And now when I integrate, I get y cubed over 3 plus a y equal minus x plus a constant, and we'll call this constant b. And we can multiply through by 3 if we want to, and we'd get y cubed plus, now 3a is going to be a different but an arbitrary constant, y, and I'm multiplying by 3, so I get a negative 3x on the right hand side, but let's transpose it, and it becomes a positive 3x, and then 3b is just a b, so we can, if we want to, maybe leave it in that form right there. And well, that is not explicit but implicitly the solution to the differential equation. And again, you can verify that yourself by substituting y and its derivatives into the original differential equation. So we found two methods today for taking an second order differential equation, and if either the independent or the dependent variable is missing in those, they become reducible second order equations, and we can reduce those equations to a first order and solve the first order, which results in another first order differential equation, which we solve again. And a characteristic would be two arbitrary constants, because we started with a second order equation, and in the example we just finished, you see that we've got a and b in the general solution as arbitrary constants, and so all of that checks out. So here's two examples then of the reducible second order equations for you to study on. I have posted more homework problems, and we will get together later this week. So thank you very much.